from the University of Wollongong in sunny Australia, between the mountains and the sea, we're bringing you a symposium on spectral noise in the human EEG, explorations in clinical and subclinical samples. This was organised by myself, Robert Barry, and Francis de Blasio. We're mainly going to talk to you about pink noise in the human EEG spectrum, which is an increasing focus in the recent literature. The aim of this series of studies has been to improve the description and quantification of brain oscillations, such as alpha and beta waves. We know that for either waves or spectra, when we observe these, we're actually seeing a mix of oscillations and noise. And that to get to the oscillations, we need to get rid of the noise out of our observed either waves or spectra. Early this year, Barry and de Blasio presented a paper that pointed out that previous efforts in this regard had been methodologically flawed, and that they in fact were violating physical principles, and that these led to overestimates of spectral noise and flawed estimates of brain oscillations. Here we demonstrate a new valid approach called Porn Extra and explore its implications for the EEG field in a range of typical and atypical groups. So in this symposium, there'll be 3 presentations. The first is by myself, which will sketch the background to Porn Extra and provides a new example of its use in normal resting human EEG. Next is a presentation by Dr. Jessica Mills, which examines a sample with clinical depression. The third and final symposium paper is presented by Dr. Francis de Blasio, who relates pink and white noise to scores on impulsiveness and the BIS-BAS scales. So this is our first talk in the symposium. I'm Bob Barry, and this talk was developed with Francis de Blasio. Its focus is on pink and white noise in the normal resting human EEG. As an overview of what I'm talking about, I'll touch on what is EEG in terms of oscillations and non-oscillations. And we can represent these either in the time domain as waves or in the frequency domain as spectra. And we'll move backwards and forwards through the talk between these 2 domains. Now, there are 2 main forms of noise in the human EEG, pink noise and white noise, and I'll describe both. Then I'll have a brief overview of the historical problems in the literature attempting to estimate pink noise, and then touch on a new algorithm for a valid estimate of pink and white noise that we developed earlier this year, or published earlier this year, and then finally finish up with future opportunities that this new algorithm provides to the field. Okay, let's go. So resting state EEG, as we know, is scalp recorded brain activity. It's the best we can do to get to the brain activity of the intact skull. And this often comes as either eyes closed or eyes open resting EEG. We often discuss this as a mix of waves or oscillations within distinct frequency ranges, such as delta, theta, alpha, beta, and to a lesser extent, gamma. But this commonly ignores non-oscillations, which is commonly considered as noise, and these noise forms coexist with oscillations, and they can be summarized in a frequency spectrum, such as this. This is a power spectrum from resting EEG in normal university students. And this shows power on the Y scale as a function of frequency on the X scale. And the bands delta, theta, alpha, and beta are marked on the plot. So this is an observed spectrum. It has this characteristic spectral morphology, moving from a large power at low frequency to a smaller power at high frequency in a sort of exponential decay with a big mountain in the middle called alpha. Now, we previously took this whole spectrum as reflecting oscillations, but we're now more conscious and aware that this is really a series of oscillation peaks floating on a noise spectrum. So most of which is below the observed spectral line is noise. Now, there are well-defined noise forms in the EEG. The first and most important for us is pink noise, which dominates the spectral shape. So here's our spectral shape again, and this dashed line represents pink noise. The definition of pink noise is that the power is proportional to 1 on F. So 1 on F, if F is large, say getting towards the beta end of this spectrum, 1 on a large number is a small power. And as we go to the low frequency end, 1 on a small number is a large power. And we can see this showing up in this dashed pink line. Now, by the 1990s, it was generally accepted in the literature that this was underlying the EEG spectrum. It was initially considered as just noise and a nuisance to be removed so that we could get a better handle on the oscillation spectrum. There's also in the EEG spectrum white noise. Its definition is that power is a constant across frequency. So we could plot that as this low-level dotted line in blue, and this is likely also to be present with pink noise, not really as dominant in power. As I mentioned before, we can think of these features in terms of either waveforms or spectra. And on the left in this series of plots, I have a plot of amplitude as a function of time for 2 seconds or 2000 milliseconds, scale at the bottom. And on the right, I've got spectral plots, power as a function of frequency. So if we look at these in more detail, starting at the top in alpha, on the left over these 2 seconds, we can see some alpha oscillations ranging from about 8 Hertz in the first second and changing over to about 13 Hertz in the second of this plot. And on the right, a frequency spectrum for that with power changing from about, or ranging from about 8 to 13 Hertz with a peak about 10 Hertz. The next plot shows pink noise with its waveforms on the left and power spectrum on the right. And you'll see that in addition to a lot of small power noise, this sort of stuff, we've got a lower frequency bump here, a much larger lower frequency, and another low frequency here. So we have some features that correspond to the low frequency end of the power spectrum. The third plot here shows you what white noise might look like over 2 seconds, and the spectrum that we might get of taking a mean over a number of these 2-second epochs, fairly constant over frequency and not as great as the high frequency, or the, sorry, not as great as the low frequency pink noise. And at the bottom here, we have a representation of what we might get if we combine all these. So you can see a dominant alpha frequency, but with pink and white noise bits in. And when we put these all together and look at the spectrum, you'll see that we are summing these alpha, white noise, pink noise, white noise together, and we can see that we have the oscillation from alpha floating on a noise spectrum. So coming back in detail to pink noise, because pink noise is proportional to 1 on frequency, if we plot these on a log power versus log frequency plot, we get a decreasing straight line, which can be used to help estimate pink noise. It should have a slope of -1. And that, as I said, can estimate the pink noise. So if we look at the spectrum in the top plot as a function of log power versus log frequency, we can see we get this strange shape, and take a regression line through that, and we get a straight regression line. But this has a slope of not quite -1. And Walter Pritchard in 92 was the first to note that it's really the alpha peak that's destroying that linearity, so that we're not getting a slope of -1. We get a deviation from that because of the alpha bump distorting the spectrum. In this case, we have a slope of -1.18. So over time, following Pritchard, a lot of research tried to fit linear regression lines to the spectra, but they avoided alpha or alpha plus beta. Here I've plotted the same spectral shape, but with a dotted line through the alpha band, and you'll see that we get, if we fit a linear trend to that, we get a regression line with a slope of -1.1, which is closer to -1 than we had with the original log power versus log frequency. So Pritchard's right, the biggest distortion is due to alpha. If we can get rid of that, it gives us a better estimate. So a lot of research did this sort of, showed this approach over time. So when we do that, we eventually start noticing problems. The most common problem was that most reported slopes that weren't -1, such as the -1.1. But still, you may be able to use this to estimate pink noise, but it's obviously not pure pink noise. It's still distorted to some extent. And the literature began to talk of 1 on F like noise rather than 1 on F or pink noise. And it appears that this is because although they were trying to get to 1 on F, the methods they were using didn't quite make the cut. They got to 1 on F like noise. There are other problems in the literature because some authors plotted log power versus frequency instead of log power versus log frequency. So if we do that, as I've done here in the bottom plot, then when we fit the line, even if we leave out alpha, then we don't quite get anything that makes much sense, because the slope is really meaningless. I've asterisked this slope here. It's minus 0.05, which is a long way away from -1. And there's no idea what it does mean. It tells us what the slope of a line going through log power versus frequency is, but it's just not making much sense. It's also really an invalid fit, because if we take this pink noise estimate, this dashed line, away from the observed power to get an idea of what the oscillation is, then we start getting problems, because if the pink noise is greater than the observed, which is supposed to be the sum of pink noise plus the oscillation, we get into an impossible situation, because when we try and get the oscillation by subtracting the pink noise away, because remember, what we see, the observed, is the sum of noise and oscillation. If we take away this estimate of pink noise, then we start getting impossible results, because here in the two places in the spectrum where I've put the blue asterisk, we actually have impossibility, because the pink noise, after subtracting from the observed, we are getting an estimate of oscillations in those regions that are negative. And oscillations can never be negative, because what we have is, in the oscillation power comes from squaring the oscillation magnitude. When we square a real number, the oscillation magnitude, we must have a positive result. Oscillation power that's negative is physically impossible. The other problem is that all these efforts ignore white noise. Now, the methodologies that have evolved in the literature, the most commonly used currently is called FOOF, for fitting oscillations and 1/f. Now, this is a product from the Wojtek group at the University of San Diego, and they're most active in the field. They've done numbers of studies estimating pink noise in different groups and different conditions, and they have a newer version that's called Spec-Param, because they're trying to get spectral parameters out of the observed data. It's a laudable ambition, but unfortunately, although they have a MATLAB toolbox available, which facilitates its use, it derives a 1/f-like noise, which they now call aperiodic fit. So they've given up talking about 1/f noise or pink noise, and they talk about 1/f-like or aperiodic fit. Note that there's no theoretical basis for this. As I said earlier, it appears the literature tried to get an estimate of pink noise, failed, and settled for an aperiodic fit rather than pursue the 1/f noise. And this continues the above problems, including problems of negative oscillatory power. So earlier this year, Barry and de Blasio published a paper, so you can get it from this source, which pointed out these issues and presented a new algorithm, which was demonstrated with simulated and real data, that extracts a valid estimate of both pink noise and white noise from the EEG, And this is called pawn extra, which is derived from pink and white noise extractor. Now, pawn extra is an alternative methodology for FOUF that has the benefit of being valid. And I'll demonstrate that in the present study. Our method here was to compose a mix of oscillations, pink noise and white noise, to form a simulation that we submitted to both FOUF and pawn extra. And we compare the outputs here. We also decomposed a new EEG sample from 20 university students who were all right-handed, mostly female, typical university students in Australian psychology. We recorded resting eyes closed and 2 blocks of eyes open EEG. We had 2 minutes in each condition in the order of eyes open 1, eyes closed, eyes open 2. This is a typical order we use so that if we average the eyes open, it is equivalent in time to the eyes closed. So if there's any systematic shifting over time, that washes out that shift. We had 30 electrodes, record EEG to 1000 Hertz, formed 2-second epochs, artifact them as usual, which you can find in any of our studies, and did FFTs to derive mean EEG spectra for each subject in each condition. So the results in our simulation, we formed this simulation input, which consists of an input pink noise, which is this dashed sort of exponential line, input white noise, which is this sort of dotted horizontal line here in the frequency spectrum, and our input oscillation, which is this black line. We had some delta activity, some theta activity, some alpha activity, a lot of alpha, and a little bit of beta. We mix those together and get this input simulation curve shown as the gray line here. When we plot this data set as a function of log power versus log frequency, we return the pink noise as a straight line with an equation here with a slope of -1. This is the intercept in log terms. And we have white noise, which has negative log power, not negative power. The power is positive up here, but taking it on log scale, we have a negative value of log power for white noise, but it's constant over frequency. And we put this input simulation into FOUF. Here is the solution we obtained from FOUF. We get an estimate of the aperiodic noise as this dashed line, aperiodic noise. And when we take that away from our input simulation, we get this estimate of the oscillation. And we've indicated here the negative power problem. We get negative power in the oscillation between delta and theta, and between theta and alpha, and between alpha and beta, and beyond beta. So we get 4 areas of negative power, which I pointed out as impossible physically. When we plot that on a log power versus log frequency plot, you'll see the aperiodic slope is certainly not pink noise. It's -0.07. So it's a dashed straight line with a slope of -0.7, which is not pink noise. Doesn't claim to be, it's aperiodic noise, but it's certainly not pink. when we look at the output from Pawn Extra, we get power versus frequency spectra that appear to be identical to the input on the upper left plot. And when we plot that as a function of log power versus log frequency, you'll see we get out pink noise with a slope of -1. Now the intercept is not quite what we put in. Instead of 728, we have 724. So we have a slight variation. And the white noise, although its log power is -0.64, we only got -0.63. So it's within 1% or so for white noise, much closer for pink noise, but solutions are all valid and not bad estimates actually. So in other words, our simulation FOOF overestimated the noise, which wasn't pink noise anyway, and underestimated the oscillation, including negative power, which is physically impossible. So it didn't do much of a job. Pawn Extra, in contrast, closely estimated the input pink noise, white noise, and oscillation, gave valid and quite accurate estimates. What happens when we turn to the real EEG? Noise topographies that we obtained for mean pink and white noise in each condition, looking at the power over 2 to 24 Hertz. The results in topography were broadly similar to what we'd previously obtained. The pink noise largely central and midline, with more in the eyes closed condition than eyes open. White noise was widespread, and topography, but not intensity, differed between eyes closed and eyes open. So we're moderately happy with that. So in other words, our simulation for pink noise, the algorithm separated the input spectral mix into its constituents, very close to input values, demonstrating that we have a valid algorithm. With real EEG, we got noise topography similar to previous samples, showing eyes closed, pink noise greater than eyes open, and similar noise levels for white noise with some topographic changes. And these roughly matched previous eyes closed, eyes open differences, suggesting that we have a useful tool for advancing EEG research. In future opportunities that arise from the use of these estimates, well, using Pawn Extra, we can get better estimates of oscillation, because previously we summed these together with noise. Now we can separate these so that this gives better oscillation estimates. We now know that it's what we have as oscillations between the pink noise estimate and our observed power. And we can do this without that noise being included. So in early days, if we looked at theta, which is important, particularly in the ADHD arena, we would be including in our estimate of what's under the curve there, we would include this large amount of pink noise. So what's shaded blue here is the real theta estimate, suggesting that without noise, we would have a very different estimate. And this means a lot of our early work on things like theta beta ratio in ADHD needs to be redone more accurately. We can also examine pink noise and white noise as new variables to explore in this field. And we can begin playing with individual differences. That has not previously been done with valid noise estimates, but in the next two talks in this symposium, we'll begin that exploration. So thank you for your attention during my talk here, and I hope you enjoy our next two talks.
Thanks so much for that, Bob. So my name is Jessica, and today I will be presenting about pink and white noise in major depressive disorder compared to healthy controls. So to briefly reiterate from Bob's presentation, following the increased recognition that scalp-recorded brain activity consists of both oscillations and non-oscillations, pink noise in the EEG and its functional correlates have been receiving increased attention in the literature. So studies have identified that pink noise is an important correlate of cognitive control and related elements such as task performance, parasomnias, and healthy aging. White noise, which is of interest because it coexists with pink noise, has remained largely overlooked in such explorations. However, aside from largely invalid pink noise estimates, an important feature of current noise literature is that existing studies have largely been conducted in healthy populations. So this focus on healthy populations does raise questions about the potential role and utility of pink and white noise in clinical groups. It is becoming a priority in the clinical research space to identify biomarkers or biologically based risk factors that can objectively identify and classify psychopathology and its severity. So if such biomarkers are detected, they may be used to help guide the selection of appropriate prevention or treatment measures, or potentially tailor intervention approaches. So as they are biologically based, spectral noise has the capacity to act as a biomarker for clinical disorders, but this possibility hasn't been properly examined in the literature. So to this end, one 2018 study found that steeper 1/f-like slopes were more closely associated with schizophrenia than traditional frequency bands and behavioral symptoms. Similarly, a 2019 study found that 1/f-like activity was a marker for treatment responsivity in depression following deep brain stimulation. So while these studies provide support for pink noise as a biomarker, these studies use FOOF and so should be interpreted cautiously. However, related to the depression study, this was only done in a small sample of older adults with treatment-resistant depression, which represents a very small subset of depression and is therefore not representative of the condition more broadly. In addition, measures of clinical symptoms were not considered. So these limitations warrant more comprehensive investigations into pink and white noise in depression, which is the focus of my talk today. So for context, major depressive disorder, or MDD, is a multifaceted and heterogeneous affective condition characterized by marked changes in mood, which is often accompanied by cognitive deficits, behavioral changes, and an increased risk of comorbid conditions such as anxiety. So MDD is recognized as a leading and increasing cause of global morbidity and mortality, with global prevalence rates of the disorder increasing annually. Reflecting its morbidity, a growing body of evidence indicates that more severe depressive symptoms are linked to a poorer quality of life, greater disability across multiple domains of functioning, and poorer treatment outcomes. So given that MDD poses such a great public health concern, there is an increasing need to identify biomarkers of MDD. Such biomarkers may be used to help predict the likelihood and severity of a depressive episode, indicate the need for early preventative measures, or help guide the selection and tailoring of appropriate depressiogenic treatments. Collectively, if such biomarkers are applied, they have the capacity to improve quality of life and prognoses of affected individuals. So while previous depressiogenic biomarker research has tended to focus largely on either genetic or neuroendocrine factors determined from blood samples, there is a growing interest in potentially non-invasive electrophysiological biomarkers of MDD. So EEG studies comparing spectral band power have found that MDD is associated with increased global power in delta and gamma compared to controls. In contrast, several studies have found that diagnostic differences in spectral bands are brain region specific, including increased alpha, theta, and delta activity in central parietal or occipital parietal areas of depressed individuals compared to controls. It has also been suggested that the overarching presence of greater slow wave activity in the form of theta and delta is thought to reflect decreased cortical activation in MDD. So aside from spectral power, other depressiogenic studies have focused more exclusively on alpha asymmetry, with several studies finding left frontal asymmetry in MDD compared to controls. However, meta-analyses indicate that alpha asymmetry is not a significant predictor of MDD as a disorder, and rather appears more closely related to specific symptoms such as mood swings and anxiety. So in recognition of the fact that EEG consists of oscillations and non-oscillations in the form of noise, aside from the investigation using FOOF mentioned earlier, there is a significant paucity of research investigating pink and white noise in MDD. So given that spectral noise is substantial in lower frequencies and its links to cognitive control and sleep regulation, spectral noise may be of relevance to MDD and its symptoms because MDD is associated with increased slow wave activity and disturbances to symptoms like emotion regulation, executive functions, and sleep. However, no study to date has used a valid pink and white noise quantification approach. So the aim of this study was to use Porn Extra as an improved and valid method of pink and white noise extraction to compare pink and white noise estimates between individuals with MDD and healthy controls, and then subsequently correlate these noise estimates with measures of depressive and anxiety symptom severity. So in line with previous research, we hypothesized that spectral noise estimates would be higher in MDD compared to controls, and that the estimates would correlate positively with symptom severity scores. So this study forms part of a broader investigation into electrophysiological biomarkers of MDD. Depressed and non-depressed participants were recruited via social media, and for this study resulted in a final sample of 30 MDD and 30 age and sex matched controls. To participate in the study, depressed participants were required to meet DSM-4 criteria for a current depressive episode, have a score above 19 on the Beck Depression Inventory, and have no comorbid psychiatric conditions other than anxiety or a personality disorder. Stable treatment with antidepressants or therapy was permitted. Controls were required to have an absence of a depressive episode, also confirmed using DSM-4 criteria, and a score below 14 on the BDI. It was a requirement across both groups to have normal or corrected to normal vision, no history of neurological illness, have no current or recent use of a supplement to enhance cognition or mood, and have no history of substance use or alcoholism. So for the procedure, on arrival at the university, participants completed a series of interviews, including the mini international neuropsychiatric interview to confirm or exclude a current depressive episode. Participants then completed the Beck Depression Inventory and the Hamilton Anxiety Rating Scale before being seated approximately 80 centimeters from a 19-inch LCD computed monitor and fitted with a 64-channel stretch lycra silver chloride electrode cap. Electrooculogram was recorded from 4 facial electrodes, and EEG was recorded using Neuroscan Acquire software and Synapse 2 amplifiers. All impedances were below 5 kiloohms prior to commencing. So EEG was grounded to an electrode placed between FZ and FPZ and re-referenced to an electrode between CZ and CPZ. All EEG was also linked to both mastoids for offline re-referencing. All data was recorded in DC mode using 16-bit AD conversion at 1000 Hertz. Eyes closed resting EEG was recorded for a total of 15 minutes before participants completed a series of experimental tasks not discussed here. So offline EEG analysis was performed using Scan 4.5, and all data was re-referenced to linked mastoids before EEG artifacts were removed using the RAAA method. All EEG recordings were manually inspected and visibly bad channels were interpolated. The EEG was then bandpass filtered from 0.5 to 45 Hertz using a zero phase shift filter. And after a 1-minute offset, consecutive and non-overlapping 2-second epochs were obtained from the subsequent 3-minute recording period before discrete Fourier transforms were applied to compute spectral power at 0.5 Hertz resolution. So all spectral data within the 2 to 24 Hertz range at each electrode was submitted to the Porn Extra algorithm, resulting in 1,860 cases for which all solutions were resolved. Total pink and white noise power were then extracted for the noise solutions at each electrode, and then global averages across the scalp were calculated for both. So the dependent variables of interest for this current study include global total pink and white noise estimates averaged across the scalp, in addition to BDI and Hammer scores. Mann-Whitney tests were performed to compare the dependent variables of interest between diagnostic groups, and Spearman's rank correlations were determined for relationships between variables. An alpha of less than 0.05 was considered statistically significant. And because we predicted that spectral noise would be higher in MDD and positively associated with psychopathology, one-tailed hypotheses were used. So in terms of participant characteristics, participants were aged between 18 and 51 years with a mean age of 26. There were 19 female and 11 males in both MDD and control groups. For the MDD group, 13 individuals reported using an antidepressant medication for at least 2 weeks prior to the EEG recording, and 18 individuals had completed at least 2 sessions of CBT. No significant differences between treated and untreated MDD participants were identified, and so all further analyses were performed with the MDD groups combined. In addition, no participant in either diagnostic group reported cannabis or psychotropic substance use within 5 days of the EEG recording. So as to be expected, both depressive and anxiety-related symptomology was significantly higher in individuals with MDD compared to controls. And in terms of spectral noise, as evident in the figure, total power across the scalp in pink and white noise were higher in individuals with MDD compared to controls. This elevation in MDD was significant for pink noise and approached significant for white noise. So this figure demonstrates the topography of the pink and white noise distributions. So in relation to the pink noise, the contour lines suggest that the distribution of pink noise across both diagnostic groups was similar. However, there appears to be increased activation in the frontal regions of the MDD group compared to controls. The difference in pink noise estimates between groups was found to be localized around the vertex. For white noise, the contour lines suggest a different distribution of white noise across groups. For controls, the white noise appears to be more localized to the vertex, whereas in MDD, it appears to be more occipital with slightly more activation in this region also. So following the significant elevation in pink noise in MDD, global total power in pink noise was correlated with depressive and anxiety symptom severity with positive associations identified. Correlations were performed in the total sample for statistical power and to account for the distribution of psychopathology scores between groups. Correlations with white noise were not performed because power did not differ significantly. So this study provides new information about the links between spectral noise and MDD. Higher pink noise estimates in individuals with MDD compared to controls is consistent with previous studies reporting increased global slow wave activity in MDD, including theta and delta. So considering that pink noise is substantial in lower frequencies, this finding suggests that pink noise may underpin or potentially drive previous theta and delta results in MDD, and that pink noise estimates may act as a biomarker that differentiates MDD from healthy controls. So that white noise that did not differ between diagnostic groups suggests that white noise may not have a significant role in MDD. So higher pink noise estimates were also associated with depressive and anxiety symptom severity, consistent with the hypothesized role of pink noise in several processes that are dysregulated in MDD, including emotional stability, cognition, and sleep. So taken together, this suggests that greater pink noise in the EEG may be more prone to experiencing greater depressive and anxiety-related symptoms. So the findings from this study suggest that greater pink noise estimates may be a clinically relevant marker for MDD and its symptoms. So as this is the first study to use a valid approach to estimating spectral noise in MDD, this leads to several directions for future research that warrant exploration. So given the possibility that pink noise may act as a driving factor towards the slow wave differences observed in MDD, it would be of interest to ascertain whether noise-corrected EEG remains associated with MDD or whether pink noise has a greater role in MDD than previously considered. So while this study identified that pink noise is associated with depressive and anxiety symptoms, longitudinal research in larger samples is needed to determine whether pink noise estimates can predict current or future psychopathology. Relatedly, future MDD research would benefit from including a symptom-level analysis of the links between MDD and pink noise to ascertain whether it is linked to specific symptoms of MDD, such as mood, cognition, and sleep, as opposed to overall symptom severity. And such investigations are important and do have the potential to confirm pink noise's utility as a biomarker of MDD, which, if applied, may greatly improve the diagnosis and subsequent treatment of the disorder, and in turn improve the prognosis of affected individuals. So we are in the process of preparing this study for publication, but I have included some references for reference. And thank you for your attention.
My name is Frances de Blasio, and I'm going to be presenting the last talk in our symposia today. I'll be looking at pink and white noise in resting EEG, a marker for behavioural activation and inhibition. So as Bob and Jess covered, pink and white noise has been receiving more interest, especially now that we've got a valid quantification tool. And we've seen in our earlier study that pink and white noise tend to differ in topography and in relation to their eyes open, eyes closed resting effects. This suggests that there are several neural origins for each of these noise sources, and that they may also differ in their functional significance. In previous research using other techniques such as FOOF and other 1/f offset type measures, positive associations have been reported between that 1/f pink noise or offset activity and MDD severity, symptom severity, as just presented by Jess in the last talk, as well as, so that's using our valid quantification technique, PornExtra. But previous research has also reported using other measures, other quantification techniques, positive associations between that 1/f or pink activity and proactive control processes, looking at error conflict rates, as well as cognitive processing speed. So the average processing speed and the proneness to making slow reaction time responses. And in a lot of this research, white noise has been pretty much largely overlooked to date. So in the present study, we're interested in seeking functional correlates of pink and white noise, specifically extracted using our PornExtra algorithm. So with this new valid quantification, this should give us better estimates of this noise and should allow us to get better insights into any functional significance that they may represent. So our interests here were threefold and largely exploratory. So following on from Jess's investigation in a clinical population, we were wondering if there are any functional associations between pink and white noise in subclinical anxiety and depression states or severity. And we're interested specifically in looking at the hospital anxiety and depression scale to quantify these subclinical anxiety and depression scores in healthy undergraduate university students. We were also interested to look at some of the personality behavioral constructs, such as impulsiveness. So some of the previously reported associations in relation to the 1/f or pink activity and cognitive control and that response speed suggests that there is a link with behavior. So having a look at the personality behavior construct might give us some indication as to the functionality underlying that association. So here we're looking at the Barrett impulsivity scale to quantify that, that personality behavior construct of impulsiveness. And lastly, we thought we'd consider motivational systems that underlie behavior, again, to see if there's any apparent functional significance associated with these two noise variables. And for this, we use the behavioral inhibition system and behavioral activation system scales, or the BIS-BAS. In this study, we recruited 52 young adults, and these were right-handed undergraduate psychology students at the University of Wollongong. They were aged between 18 and 33 years with a mean age of 20.6. So a fairly typical young adult population. 16 of our sample were male and 36 were female, and they were screened for things including head injury or trauma resulting in long-term impairment, a history of seizures and or psychiatric illness, psychoactive drug use, and they also reported abstaining from caffeine for 12 hours prior to the recording session. Our participants came in and completed the HADS, so the Hospital Anxiety and Depression Scale, the Barrett Impulsivity Scale, and the BIS-BAS Behavioral Inhibition Activation System scales. Following this, continuous EEG was recorded during consecutive 2-minute blocks of resting with eyes open, eyes closed, and then a second eyes open block. While the participants were resting, this continuous EEG was recorded at 30 scalp sites, as well as 4 EOG facial electrodes. The data was recorded reference to the left mastoid and was later re-referenced offline to the average mastoid. So the second right mastoid was recorded as a separate channel to allow this. And the data from DC to 30 Hertz was sampled at 1000 Hertz. For our power spectra quantification, our recording was first EOG corrected using the RAAA procedure. The data were then re-referenced to the mean of the mastoids. Manual inspection was used to identify visibly bad channels, and these were interpolated, and no more than 3 individual channels were interpolated for any individual participant. 60 consecutive 2-second epochs were then extracted in each 2-minute block. And these then underwent a 3-step automatic artifact rejection procedure similar to that used in Foti et al. 2009. So in this 3-step procedure, we removed any epochs that had extreme amplitudes beyond plus minus 75 microvolts. Keep in mind, this was also applied after a DC correction of those epochs. The second of the 3-step procedure was seeking any epochs that had an extreme voltage jump of greater than 50 microvolts between adjacent data points, or a flat line indicated by a voltage change of less than 0.5 microvolts in any 100 millisecond period. A 10% Hanning window was then applied to the remaining accepted epochs in each block, each condition. And these single-sided power spectra were derived using discrete Fourier transforms. So this was extracted at a resolution of 0.5 Hertz, and a window correction was applied immediately following that extraction. In order to quantify our pink and white noise, we then submitted the within subject mean spectra between 2 and 24 Hertz to our PornExtra algorithm. So in this instance, we submitted 4,680 cases. So this is the data for 52 participants at each of the 30 electrodes for, across the 3 blocks. And for our extracted pink and white noise solutions, we then computed the total power across that 2 to 24 Hertz range. We extracted that at each electrode, and then we computed the global mean across all of those 30 electrodes for the eyes closed condition, as well as then for our mean eyes open blocks. In terms of our statistical analysis, in order to seek associations between our pink and white noise measures and each of our measures of interest, we used 2-tailed Spearman's rank order correlations, because these were largely exploratory. And at this point, we didn't correct for multiple testing due to the exploratory nature of this study. In terms of our results, we did find valid pink and white noise solutions for all 4,680 cases that were submitted to our algorithm. And we received topographic distributions that appeared quite consistent with our prior work. So here we can see pink noise on the top row and white noise below. We've got our grand mean across the conditions and participants, and then we've got our participant mean, so our cross participant mean for each individual condition. So we can see, as Bob mentioned in his first talk, that we tend to see increased pink noise in eyes closed compared to eyes open, whereas for white noise, it tends to be comparable between eyes closed and eyes open with perhaps some shifts in topography. In terms of our pink noise correlations, we did find a significant correlation between eyes closed pink noise and our Barrett impulsivity scale perseverance subscale. So here we can see we have plotted the rank orders for our BIS-11 perseverance scores and our rank orders for our total global total pink noise. And we can see that this was an inverse correlation. When we looked at our eyes open pink noise data, this showed no significant correlations with any of our assessed measures. So all of the significance values were greater than or equal to 0.066 two-tailed. In terms of our white noise results, we found our eyes closed white noise data correlated with the BAS, so the Behavioral Activation System Drive subscale. And we can see here again, we have our ranked BAS drive scores plotted against our ranked global total white noise. And we can see this time it was a positive association. So higher rankings in total global white noise were associated with higher rankings in the BAS drive scale. In the eyes open condition for white noise, we found significant correlations with the Barrett impulsivity scale perseverance subscale. This was an inverse correlation. We also saw an inverse correlation with the Barrett impulsivity scale motor subscale, motor, which is the second order factor. So that comprises of the perseverance and first order motor subscales. So similarly, we've got the inverse association with the perseverance subscale, which is a subscale of that motor factor, which again was also an inverse relationship. And then lastly, our eyes open white noise correlated with the behavioral inhibition system. And again, that was an inverse association between those measures. So interestingly enough, our subclinical anxiety and depression scales using our hospital anxiety and depression scales, we saw no significant associations with either pink noise or white noise in any of our resting conditions, so in eyes open or eyes closed. So for our correlations with our pink noise data, all of our p-values were greater than or equal to 0.691, and for our white noise, they were greater than or equal to 0.87. So there was no approaching significance and no apparent association between either of these noise variables and subclinical anxiety or depression scores in this sample. In terms of our impulsiveness scale, we did find that both eyes closed pink noise and eyes open white noise each inversely were associated with the perseverance subscale. Now, the perseverance subscale of the impulsivity scale is a subtrait of the second order motor factor. And this particular scale, or this perseverance subtrait, is associated with consistency or stability in lifestyle. We also found that the eyes open white noise was also inversely associated with that second order motor factor. And this second order motor factor is associated with acting without thinking. So together, this suggests that higher eyes closed pink noise and higher eyes open white noise are each associated with lower motor impulsivity. And impulsivity has been related to and reported to interact with processes of both attention and executive function. So this provides us with some consistency with the reported associations between 1/F activity and processing speed. Now, in that particular study, increased pink noise was associated in rest, so both eyes open and eyes closed, was associated with the tendency to have an increased mean reaction time and a tendency more so to make slower responses. So hence the reduction in that impulsivity kind of being consistent with that increased reaction time from prior studies. In relation to our behavioral inhibition and activation systems, we saw that eyes open white noise was inversely associated with the with the behavioral inhibition system, and this system is associated as being showing a sensitivity to anxiety-provoking stimuli and being predictive of nervousness in response to cues of impending punishment. Activation of this system, this inhibitory system, is associated with the inhibition of movement towards a goal. We also saw in eyes closed white noise, a positive association with the behavioral activation system, specifically the drive subtrait or subscale. This system was designed to be sensitive to reward and specifically to the pursuit of desired goals. It was developed to be predictive and has been tested and shown to be predictive of positive affect in response to cues of impending reward. And activation of this system has been associated with the movement towards goals. So overall, what we're seeing in relation to our white noise and these systems is that increased eyes open white noise shows an association with less goal-directed inhibition, whereas increased eyes closed white noise has shown an association with more goal-related activation. So we're seeing an interesting pattern that's differing between the eyes open and eyes closed conditions in relation to white noise and these motivational systems. Okay, so there were a few limitations of our current study. So this is very preliminary research, and due to the exploratory nature, we didn't apply any corrections for multiple testing. However, this should be considered and applied in future replication studies that try to see if we can replicate these particular findings. There was little correspondence between the impulsivity and the BIS-BAS outcomes. So there have been some suggestions in the literature that impulsivity being an orthogonal trait to anxiety, that each of these systems, so the anxiety and impulsivity, may be reflected and load in with the behavioral inhibition system more so for anxiety and the behavioral activation system more so for impulsivity. But there are a bit of controversy and not everyone's in agreement as to the association between these measures, and we saw very little association here. So this also potentially could be perhaps due to the absence of motivational tasks or motivational stimuli. So because we've just got our resting state data, this may not be sufficient to tease out differences or impacts or relationships between these measures. Task-related pink and white noise may also prove to be more insightful. So we've looked here at pink and white noise in resting state to see if they have any apparent functional correlations with these different constructs, so impulsivity, the behavioral inhibition system, and the behavioral activation system. However, if we were to quantify pink and white noise in a particular task where there may or may not be motivational stimuli, this may potentially give us different insights and may be a more insightful measure. So in conclusion, our results do appear quite promising, and they do suggest that our eyes closed, eyes open pink and white noise differentially relate to impulsivity and to the behavioral inhibition and behavioral activation system and motivational systems. And these associations likely contribute to the observed differences in cognitive control that have been reported in the previous literature using different quantification techniques. So this suggests that there is value in seeing if we can replicate these findings, particularly using these newer, more valid quantification techniques, specifically our Porn Extra algorithm. And if we get a better understanding of the functional significance of these noise estimates, so our pink and our white noise types, then as Jess mentioned, this will potentially provide valuable biomarkers for various conditions. Thank you.
Well, thank you for listening to our presentations. So I hope you've enjoyed the 3 talks today. If you're interested in our Porn Extra software, you can send me an email and I'll supply it to you. So thank you for your attention.